The next topic that I want to talk about is parametric equations. So far in what we've done in calculus, most of our graphs have been described by this kind of equation, y equal f of x, meaning that a single x in produces at most one y out. Now, you'll remember that this means that the graph has to obey the vertical line test. Even if there's a gap or a sharp corner, no x can produce more than one point on the graph. This is a serious limitation because many graphs don't act that way. We will get around to this restriction by thinking about this a different way. I'm going to have not y as a formula involving x, but we're going to have some other variable named t, which we'll call the parameter of the problem. And we're going to determine the x coordinate as some function of t and the y coordinate as some other function of t. And this will be how we're going to get the points on our graph, the x's and y's. Conceptually, this is very simple. If I actually knew these formulas, I would pick a number t, I'd calculate the x and the y to go with it, I'd plot the point x comma y, and then I would go around and pick another t value and continue doing this until I had enough points that I felt good about the picture. Of course, in practice, doing this by hand is extremely tedious. Luckily, there are things built into the calculators. So if you'll remember in one of the previous lectures or descriptions of documents, I said be sure to have your calculator with you because from now on we'll be using it fairly heavily. Now we begin doing that. I want to think of parametric equations. X equals 2 times t plus 1 and y is 4 times t minus 2. I want to show how to graph that on your calculator. We're familiar with the mode button, mainly because we sometimes have to switch back and forth from radians to degrees and so on. At the moment, that question is irrelevant to me. Set it in radians and leave it that way for now. That's not what we're up to. One of the things that's listed is FUNC, PAR, POL, and SEQ. FUNC is short for function. Y equals a function of x. Go sideways. PAR is short for parametric. And to activate that, I'll press the enter key. So moving the cursor out of the way, you can see that FUNC is no longer highlighted, but PAR is. When I go to my Y equals menu, it's going to look different than it used to. Previously, it said Y1 equals, Y2 equals, and so on, but now it's different. It says X1T, which is short for X1 of T, and Y1 of T, and X2 of T, and Y2 of T. For each graph that you want to use, you're going to have to tell it both the X and the Y coordinates in terms of parameter T. As for how we access the T variable, this button previously always was X to us. But if you look at what's actually written on the keycap, it says X comma T comma some other stuff we'll worry about later. When the calculator is set in parametric mode, this button is no longer X, it's T. So for the X coordinate on my graph, I want 2 times T plus 1. For the Y coordinate on my graph, I want 4 times T minus 2. I'm going to use the standard viewing window, and there'll be a little problem which we'll figure out how to fix. So I'm going to press zoom and 6. And my graph appears to be more or less a straight line, except I don't see anything down here. Go into the window settings. In addition to X-min and X-max and Y-min and Y-max, with which we're familiar already, there's also a T-min and a T-max. And not only that, there's a T-step as well. We won't worry about T-step right now. By default, when you say standard viewing window, it sets T-min to 0 and T-max to 2 pi. The problem with our picture is we don't have enough different T values in it. So how about I set the T-min to -5? Remember, you have to use this negative sign. I'll leave everything else alone and press graph. And then you see, I see more of the picture than I used to. It's easy to get fooled by the default window settings, especially that T-min equals 0 business. So we know how to do this on the calculator now. Secondly, is there a way that I can convert this pair of equations, these parametric equations, into something that looks like y equals f of x, which is what we're used to thinking about? That is, can I eliminate all references to the parameter t and write the connection between the x and the y coordinates directly this way? For this particular problem, the answer is yes, and it's quite easy to do. So take the equation that relates the parameter to the x coordinate. X is 2t plus 1, so x minus 1 is 2t, so t is 1/2 x minus 1/2. My other parametric equation says that y is 4 times t minus 2, and we just figured out how to express t in terms of x. Multiply through by the 4 and simplify. Y is 2x minus 4, which we know to be the equation for a straight line with slope 2 that has y-intercept -4. We have literally eliminated the parameter t. We've written this relationship in terms of something that doesn't have t in it. I'd also like to think about circles. And for convenience, I'm just going to take circles that are centered at the origin. So they look like x squared plus y squared equals r squared, where r is the radius of the circle. If I divide through by r squared, I can write this as x over r quantity squared plus y over r quantity squared equals 1. And then I somewhat facetiously say to myself, it's too bad I don't know a couple of functions that when you square them and add them up, you always get 1 for an answer. Of course, the answer to that is we do know such functions. Sine and cosine act like that. So one way that I could describe a circle would be if x divided by r is cosine t, and y divided by r is sine t, or rearranging it very slightly, x is r cosine t, y is r sine t. If you look at the relationship between the angle t, which you would have called theta probably back in trigonometry, between the line segment that connects my point, the origin, and the positive x-axis, cosine of that angle is x over r, sine of that angle is y over r, which is these same two facts. If it was convenient for me, I could think of the parameter in this problem being this angle. There are other ways I could think about it, but this is one way. Now, to be exact, x squared plus y squared equals 36. If I let x equal 6 cosine t and y equals 6 sine t for t 0 to 2 pi, this is why they picked that default, I should get a picture of my circle, centered at the origin, radius 6. So I've already gone on and typed in my x1 and my y1. I've also already graphed this on the standard viewing window. So to make it draw the picture again, I'm going to zoom and make choice number 5, which you'll remember tries to compensate for the fact the screen has more pixels sideways than it does up and down. The thing to be aware of is, where does this graph start plotting and which direction is it going in? It started on the positive x-axis, and the points were plotted by going in a counterclockwise direction. So if I wanted to represent this on paper, I would draw my circles, and I probably should draw little arrows in, indicating the orientation. Now, that's not the only way I could have done that, though. I could have made x equal 6 times sine of t and the y 6 times cosine t. If you figure out what x squared plus y squared is, it comes up equal to 36 again, so I can do my parameter a different way if I want. This is a different parameterization of the curve. Just like before, I'm going to draw the picture. Be careful to take note of where the thing starts at and which direction it's going in. Zoom 5. It started on the positive y-axis and went clockwise instead of going counterclockwise, which of course you could represent in this sort of picture. Now here's a distinction that we need to make. If I'm only interested in the points that I get, as I do this or the one before it, there is absolutely no difference between the two. I get a circle centered at the origin, radius 6 either way. If I'm thinking of t as maybe not being an angle, maybe it's time, and the x and the y are telling me the location of an object as time varies, then the physics is different. In the first version, we started on the positive x-axis and traveled around a circle counterclockwise. Here, we start on the positive y-axis and go around clockwise instead of counterclockwise. So if it's just the picture that I'm after, I don't care one way or the other. If I'm doing a physics problem, I probably do care. Even that's not the only way you could do this. You could say x is 6 cosine 4t minus 1, and y is 6 sine of 4t minus 1. If you let t vary over all real values, so does 4t minus 1. So if my range of t values is big enough, this too is going to give me my complete circle. Zoom 5. I get my circle back again. As long as I stick the same expression into this cosine and this sine, the points that I generate will obey x squared plus y squared equals 36. So instead of putting in t or 4t minus 1, I'm going to put into the cosine and sine the same quantity, but that quantity is going to be cosine of t. So x is 6 cosine of t, and y is 6 sine of that same cosine t. X squared plus y squared is still going to be 36, but something really odd is going to happen here. I'll say zoom, choice number 5. And because the little marker up in the corner has finished, it's done plotting, it didn't give me the whole circle. The first thing you think is, well, maybe it's just that the range of t-values isn't big enough. So let's give that a try. I'll make the t-min -6. That's what fixed us up before. And I'll press graph. You'll notice that it calculated a little longer, but gave us back the same picture we had before. Well, maybe it's still not big enough. So let's make t-min -12 and t-max +12. See, it's still working. It continues to work. I get that same picture back again. If you remember, one of the ways we could interpret the thing that we're feeding into the cosine here and the thing that we're feeding into the sine was the angle that connects the line segment from the origin to the point, the angle that it makes with the positive x-axis. This angle, cosine t is never bigger than 1 radian and is never smaller than -1 radian. So you're only going to get pieces on your graph that correspond to about -57 degrees up to +57 degrees. In this case, if I do the parameter this way, then this is unfortunate. This is not a very good way to do it because it only gives me a piece of the graph that I'm interested in. So some ways of doing the parameter are more informative than others are. Anyway, going back to our original setup, if I have the circle x² + y² = r², probably the simplest way to parameterize that I can think of is x = r cosine t, y = r sine t. It is for this reason that cosine and sine are sometimes called the circular functions. I won't look at this in the greatest generality, but think about the graph of x² - y² = a². Back when we did the circles, we divided through by the a² and said to ourselves, it's too bad that we don't know a couple of functions that when you square them and add them up, you get 1 for an answer, which obviously were cosine and sine. Here, if I have something of this nature, I think to myself, it's too bad that I don't have a couple of functions that when I square them and subtract one from the other, I always get 1 for an answer. There's a test question that asks you to verify that for hyperbolic cosine and hyperbolic sine. Hyperbolic cosine squared of t minus hyperbolic sine squared of t always works out to be 1, so that in the same way that we did for circles, if I let x equal a hyperbolic cosine t and y equal a hyperbolic sine t, that's going to give me the points on this hyperbola. So sine and cosine, circular functions, R2, hyperbolic cosine and hyperbolic sine, that is hyperbolic functions. That's why we call these functions hyperbolic. That's the H on the end. They are to the circular functions as circles are to hyperbolas. Now, I have to say there's another choice that's more familiar to us. You could write x equal a secant of t and y equal a tangent of t. And x squared minus y squared would still be a squared. So we've got two completely different ways of thinking about how to draw graphs of hyperbolas using parametric equations. Each one has an upside and a downside. So we'll look at that now. First, we'll look at using the hyperbolic trig functions. So I'm going to look at x squared minus y squared equals 1. To make a parameterized version of this, I'm going to let x equal hyperbolic cosine t and y equal hyperbolic sine t. If you look on your keyboard of your calculator, there is no hyperbolic cosine or hyperbolic sine. Even so, it's built in. We just have to go looking for it. So my x1, which I want to be hyperbolic cosine of t, I'm going to push the second button and then 0. This brings up a list of everything the calculator knows how to do. If you look at the keypad, up above the keys are the letters of the alphabet. C is up above this button called PRGM, which we're not going to talk about. Push the button that corresponds to C, and it jumps you down to the stuff that starts off with C. And then I can scroll down until I find the hyperbolic cosine. So x1 is going to be the hyperbolic cosine of t, close parentheses. Likewise, to get to the hyperbolic sine, I'll say second, catalog. The button that goes with the S is the natural log button. Then we'll scroll down until we find the hyperbolic sine. Y is going to be hyperbolic sine of t, close parentheses. First try, I'll put this on the standard viewing window. Well, it's interesting. An actual hyperbola has a curved piece over on this side and a curved piece over on the other side. It looks like I'm only getting 1/4 of my graph. The first thing you think of is maybe my t range isn't good enough. Go into the window settings. T max is 6.28, but T min is 0. There aren't any negative T values in the picture we were looking at. So make T min equal to -5 or something. Now I see half of my hyperbola. Unfortunately, that's all I'm going to see, because if you remember what the definition of hyperbolic cosine is, it's e to the input plus e to the minus input over 2. All values of the exponential function are positive. So this is positive. If x is described by being hyperbolic cosine of t, then there is no way for this parameterization to produce the left-hand part of the graph. Now, if you were after the points that were on this hyperbola, this would be bad news because you're leaving out half your points. On the other hand, if you were describing the orbit of a comet by this parametrization, it would be fine. A comet comes in, gets close to the sun, turns around and goes back out, and this part of the mathematical hyperbola is irrelevant. You don't even want to see it. So there are good things and bad things about this way of doing it. Oh, I should also mention the hyperbolic cosine is continuous, and so is the hyperbolic sine, because they're just combinations of e to the t and e to the minus t. What about our other idea? X equals secant of t and y equal tangent of t. I have no secant button on the calculator. I could go look for it in catalog, or I could just be lazy and say secant of t is 1 over cosine t, which is what I'll do. I do have a tangent button, so I'll use that to describe the y coordinate. I'm going to put this on the standard viewing window. Well, that's very interesting in several different ways. Let me move this up a little bit. I want to zoom in towards the origin so that it becomes a little bit more transparent about what's happening here. So I'm going to say zoom to enter. So I can clearly see I've got this part of the hyperbola, which is good. Even better, I've got this part of the hyperbola, which is good. I've got two straight lines, which, despite what you might think is not good, the asymptotes of the hyperbola cross at the origin, and that's not the origin where these places cross at. So the good news is I've got the entire hyperbola here. The bad news is there's something funny going on with that pair of straight lines. And actually, there's more bad news than that, but we'll deal with it one chunk at a time. If you press the mode button, you'll see a wide variety of options, including some plot options. The one that's activated is connected. When the calculator draws the graph, it plots a point, it plots the next point, and then it connects them with a straight line. You can do it that way, or you can go over into dot mode. This is going to plot all of the dots all right, but it isn't going to connect them with straight lines. So draw the graph again, and you only see the dots, but clearly I've got my hyperbola here, both the right-hand part and the left-hand part. But notice something. When I turned the connect thing off, those two lines disappeared, which makes me think that they weren't really ever there in the first place. I'm going to do the trace thing in a moment. Secant's 1 over cosine. Tangent is sine over cosine. Both of those are undefined at places where cosine is 0. That is to say, odd multiples of pi over 2. Not only that, if you go back and look at the graph of cosine and tangent, both cosine and tangent change sign at odd multiples of pi over 2. So if I was just a little bit less, say, than pi over 2, which is 1.57, then both of these would be positive. And also, both of them would be very big. If I increased the t just a little bit, all of a sudden, both of them are going to be negative, but still large in the absolute value sense. This is going to have unfortunate consequences for my graph. So let's do the trace thing. I'm going to push trace, and I'm going to put t equals 0 in. That puts me at the right-hand vertex of the parabola, excuse me, the hyperbola, that is. When I push the right button here, it's going to increase the t value. And what happens to the x and y depends on the formulas you're using. So I'm going to increase t a little bit. So you see I'm in the first quadrant. Increase it some more than that, more than that, more than that. T is now 1.43 some odd. The x and the y are both positive, which means I'm up here somewhere. On the other hand, 1.4 is getting awful close to 1.57, which is roughly pi over 2. Increase t a little bit more, And all of a sudden, x is -4 some odd, and y is -4 some odd. By increasing the t a very small amount, I've gone from being up here to instantaneously being over there. If this were the path of a comet, that would be real bad because physical objects don't act like that. But continue increasing the t number. There I am, down in quadrant 3. I'll increase the t numbers some more. The next odd multiple of pi over 2 would be 3 pi over 2, which I think is 4 point something. So here I am at 4.05. X is negative, y is positive, and you would think that as I continue increasing the t, I would just continue going out in the direction I'm going, but that would be wrong. Increase t some more, little more, and all of a sudden I'm over here now. Every time that t passes through an odd multiple of pi over 2, the location that I'm at is going to suddenly discontinuously change what quadrant you're in, which is not good. This is why those two straight lines were there. As you went over pi over 2 here, you plotted the last point, you increased the t a little bit, and suddenly you're teleported down here, and it connected it with a straight line segment. Those crossed straight line segments are not supposed to be there. So there's good news and there's bad news. I get the entire hyperbola, that's the good news. At odd multiples of pi over 2, the graph suddenly jumps from one quadrant to another quadrant, and I didn't write it down, but unless you're real careful about how you're interpreting stuff, you'll think that the graph includes those two crossed straight lines, when in fact, they're not even part of the graph to start with. The moral of this story is we have to be a little bit careful about the parameter that we pick in terms of what we're going to do with it. If I just want the points on the hyperbola, as long as I remember to turn connected off, this is great. It gives me the whole parabola. Hyperbola, that is. I want to set up another comparatively simple situation. I want to let x equal 3t over 1 plus t cubed. Also, y is going to be 3t squared over 1 plus t cubed. A couple of preliminary comments. If t is 0, then you're at the origin. Also, if t is -1, you don't actually get answers back for x and y because the bottom of the fractions will be 0. And also, if you let t tend to infinity, x and y approach 0. So as you allow the t to become very big, you get close to the origin again. Firstly, I want to draw the graph of this thing, as we've done before. Secondly, I want to see if I can't eliminate the parameter some way. So I've typed the expressions for x and y into the calculator. I'm going to put it on the standard viewing window. Now, it's very difficult to see what's going on, but on the standard viewing window, t starts off at 0, which is going to make the x and the y both 0. You start off at the origin, and as t increases, apparently you go around in this little loop, and you don't quite get back to the origin again, but you do get very close. To try to make this look a little more clear, I'm going to zoom in. that does seem to be what's going on. And notice I've turned connect back on for now. But you could get fooled. Let me go into the window settings. Remember, by default, t goes from 0 to 2 pi. I'm going to change the t min to -6 to include some of the rest of the graph, and then draw it again. So it looked like it started here, it went off that way, then when t was 0, suddenly it jumped back to the origin, started going around in a loop, and then it did this other thing. That's very peculiar looking. Also, do we believe that that straight line is actually part of the graph? I'm going to go into mode. I'm going to go back to dot mode. I'm going to draw the picture again. Oh, I put it on the standard viewing window again. So t goes back to -6. So it looked initially like it went over here, it went around in a circle, and then there was the part upstairs. Zoom in. So you can see that there's almost a loop here, but it doesn't close up because these points never got back to the origin. This graph is much more complicated than it looks at first. And if we didn't know any better, we would think that that straight line was part of the graph. This is definitely not y equal f of x. Pick an x number here, there'll be 1, 2, maybe 3 places to go with it. So this is not the graph of any y equal f of x. Having said that, if there's a formula that relates x and y, that means it's not very simple. But I do want to see if I can't eliminate the parameter somehow. If you look at the formula for y as opposed to x, they're almost the same thing. So if you write y divided by x and work the algebra out, you find out that y divided by x is actually the value of the parameter. And we're going to be sneaky. We're going to take this fact and in one or the other of the two formulas, replace letter t with y divided by x and simplify it. So t is y divided by x. X is 3t over 1 plus t cubed. Every place I see the letter t, I'm going to write down x divided by y instead. Once I've done that, I'll multiply the top and bottom of the fraction by x cubed. By doing that, I'm going to clear out all the fractions. So this says that x is 3yx squared over x cubed plus y cubed. If you multiply both sides by the denominator, we find out that x times x cubed plus y cubed is 3 times y times x squared. Assuming that x isn't 0, you can divide through by x, and you find out that the formula that relates x and y directly is, as expected, kind of complicated. It's x cubed plus y cubed minus 3 times y times x equals 0. So this is what you get when you eliminate the parameter using the equation for x. An obvious question that somebody might ask is, what if you had used the equation for y instead? Do exactly the same thing. Y is 3 times t squared over 1 plus t cubed. So I have to multiply by x cubed to get rid of all the fractions. I find out that y is equal to 3y squared x over x cubed plus y cubed. Multiply through by the denominator. Y times x cubed plus y cubed is 3 times y squared times x. Divide through by the y, assuming it isn't 0, and you find out that x cubed plus y cubed minus 3yx is 0, which is the same equation that we had using the x formula. A hyperbola of type x squared over 64 minus y squared over 9 equals 1 can be written in the more suggestive version. The square of x over 8 minus the square of y over 3 is 1. You could write x over 8 as hyperbolic cosine t, and y over 3 is hyperbolic sine of t, and then multiplying through by the constants, get parametric equations for the given hyperbola. A more complicated example, x equals 5 sine of 2 times t, and y is 10 times cosine t. I've already put this in my calculator. Also, I've turned connect back on because it does no harm in this case. I'm going to put this on the default viewing window. And I get a figure 8 pattern. Let me square that up. That's better. It's still a figure 8 pattern. Obviously, this is not y equal f of x for any function f, because say at x equals 1, there's going to be 4 points on the graph to go with it. So this is a new shape to us. Besides looking at the graph, I'd like to eliminate the parameter. This example has been carefully rigged up to make it possible to do that. Sine of 2 times t is 2 times sine of t times cosine t. So if I use that fact, I can rewrite my x formula in this way, and the y formula remains as it was before. Notice there's a simple relationship between y and cosine t. We'll make use of that in a minute. If you write down what x divided by y is, the 10s cancel out, the cosine of t's cancel out, and all that's left is sine of t. It's too bad that that isn't written in terms of cosine t, because cosine of t is y divided by 10. So what we'll do is we'll square both sides and use the fact that sine squared of t is 1 minus cosine squared of t. Since cosine of t is y over 10, cosine squared is y squared over 100. Then clear the fractions, rearrange it. 100x squared minus 100y squared plus y to the 4th equals 0 is the xy version of the formula for this figure 8 shape. We've got to adopt a little bit of technical language here. Usually when we talk about curves, what we're really thinking in our minds is the picture that we get. But we've got to be more particular about it now. For us, a curve is going to be a set of points, the graph of the curve, but that's not all. You have to have parametric equations that produce those points. So if you look at x equals 5 cosine t, y equals 5 sine t, t between 0 and 2 pi, this is a circle of radius 5 centered at the origin. That's what the picture looks like. X equals 5 sine of t, y equals 5 cosine t, t goes between 0 and 2 pi, is a circle, center at the origin, radius 5. The picture, the graph that goes with this set of formulas and the picture that goes with this set of formulas are exactly the same circle, but technically speaking, we would say these are not the same curve because even though the pictures are the same, the formulas are not. It's a picky technical thing. I'm going to momentarily take a little side trip, which appears to have nothing to do with what we just talked about, but in fact does. I'm going to think of having x equals t squared plus 2t plus 1, y equals t minus 4, with no restrictions whatsoever on what t can be. T can be any real number at all. I want to think about what happens at t equals 0. At t equals 0, x is 1 and y is negative 4. This tells me the location that we're located at. The derivative of x with respect to t is 2t plus 2. Derivative of y with respect to t is the constant 1. So in particular, at t equals 0, dx dt is 2 times 0 plus 2, which is 2. And regardless of what the value of t is, dy dt is 1. What does that tell me? If I think about the direction that the curve is going in at time t equals 0, if I want to think of t as being time, the tangent line acts like this. For every unit increase in t, x gets bigger by 2 and y gets bigger by 1. That's what these statements mean. So I'm sitting here on the curve. I want to draw in a tangent line at this point on the curve. The thing to do is to move 2 units this way and 1 up. Locally, that looks like the curve. I want to think about a minor variation on a theme. I'm on some curve at some particular t value, maybe t equals 6 or something. X comes up 3 and y comes up 1. That tells me where I'm at. Suppose that at t equals 6, the dx dt is 0 and the dy dt is 2. What does that mean? If I increase t from 6 to 7, the x changes by 0 times the amount I changed the t. The x doesn't change at all. The y is going to change by 2 times how much I changed the t. If I increase the t to 7 from 6, that means the change in t is equal to 1. 2 times 1 is 1. Start here, increase x by 0, increase y by 2, and that's another point on your tangent line. So if the derivative of x is 0 and the derivative of y isn't 0, that doesn't mean anything bad about the situation. I can construct a tangent line. It happens to be vertical in this case. Again, suppose at t equals 6, you are located at x equal 3, y equal 1, but this time at t equals 6, the derivative of x with respect to t comes up negative 2, and the derivative of y with respect to t is 0. On the tangent line, the change in x coordinate is negative 2 times how much you changed the t value, and the change in the y coordinate is the amount you changed the t value times the rate at which y is changing on the tangent line, which is 0. So if I sit here and I increase t by 1, the y coordinate doesn't change, but the x coordinate gets smaller by 2. If dx dt is negative 2 and dy dt is 0, I have myself a horizontal tangent line. So that also is not any big problem for us. But what if, by bad luck, the derivative of x with respect to t and the derivative of y with respect to t are 0 at the t value that I'm sitting at, this tells me nothing about how the tangent line is going to act. Now, you might be thinking the only way this could happen would be if both x and y were constants, so that the graph would consist of this single point, but that's not true. It's possible on interesting graphs to have both of these derivatives come up 0 at the same spot, and yet the graph not being anything weird like a single dot or anything. We need to look at that. So I'm going to have two curves, and remember, a curve has to be a picture together with formulas that generate that picture. So curve number 1, x is going to equal t, y is going to equal t. T can take on all real values. X is t and t is y, so x and y are the same thing. The picture is the graph of y equal x, which is a straight line that passes through the origin, slope 1. Over here, curve number 2, x equals t cubed, y equals t cubed. As t takes on all real values, so does x and y. T is x cubed is y and x are the same thing. The graph for this curve is exactly the same thing as the graph for this curve. It's a straight line that passes through the origin, slope 1. Let's think about what's going on in terms of the derivatives and the direction of the tangent line. Over here, the derivative of x with respect to t, that would be the derivative of t with respect to t, that's 1, no matter what the t value is. Derivative of y with respect to t is 1. And keeping in mind what we were talking about a minute ago, if I'm sitting here at the origin and I want to get back on the tangent line, I'll go 1 unit sideways and 1 unit up. What else am I going to do? The slope of the straight line is 1 after all. So this is consistent with everything we said before. But here's the bad part. Derivative of x with respect to t on the second curve is 3 times t squared. The derivative of y with respect to t is also 3 times t squared. So suppose you're sitting at the origin and you say to yourself, I've got some tangent line. How do I get another point on the tangent line? Over here, dx dt and dy dt told me what to do. I go 1 unit sideways and 1 unit up, but here at t equals 0, 3 times 0 squared is 0. Both of my derivatives are 0 here. They don't tell me what I have to do to get back on the tangent line. So this kind of behavior, where dx dt and dy dt are both 0 at the same t value, that's extremely undesirable because it doesn't tell me things that I want to know. So we're going to make a definition for the nice case. Suppose that y and x are parametrically defined on some interval of t values from t equal a to t equal b. Not only that, the derivatives of x and y exist on the open interval from a to b, and there is no t number in that interval where dx dt and dy dt are 0 at the same time. If this happens, the word we make up to describe this good situation is, we say the curve is smooth on the interval from a to b. Basically, smooth curves are the ones that we can use derivatives to tell us about tangent lines. Going back to curve 1, dx dt and dy dt were 1 no matter what t is, neither one of them is ever 0, so it's impossible for both of them to be 0 at the same time. Curve 1 is smooth for all intervals of t numbers. On the other hand, curve 2, the derivatives are 3 times t squared for both the x and the y, and at t equals 0, both of those derivatives are 0. If I have an interval of t numbers and it contains t equals 0, this curve is not smooth on that interval of t numbers. On the other hand, if you have an interval of t numbers that excludes 0, then everything's fine. Curve 2 is smooth on the interval from 1 to 3, but it's not smooth on the interval from -3 to +3, because that includes t equals 0. It's important that you understand smooth is a technical idea. If you just look at the pictures, you cannot tell me if a curve is smooth or not. Based on the 2 examples we have so far, being not smooth, it could be that that's not the fault of the graph. It's not the fault of the set of points. It could be that we've just picked our parameter in an unfortunate way. You might go away from that thinking that that's the only thing that can happen, but sometimes you will have a non-smooth curve, and there really is something funny about the graph. So I want to look at that now. I'm going to look at x equals t squared and y equals t cubed. It seems nice enough at first. X and y are polynomials in terms of t, but thinking of our curve 2 example, we have no confidence in that. Dx dt is 2 times t. Dy dt is 3 times t squared. Both of those derivatives are 0 when t is 0. So there's one spot that you have to exclude from an interval if you want to have a smooth curve, and it's t equals 0. Now, naturally, at t equals 0, x is 0 squared, which is 0. Y is 0 cubed, which is also 0. The place where I have non-smoothness is the origin. If you use your calculator to draw the graph of this thing, it starts off down in quadrant 4. Be sure to include some negative t numbers. It's going like this for a while, and then suddenly, very abruptly, it changes direction and starts looking like an upward opening parabola almost. It isn't one, though. The problem here is, if you were to zoom in on that, it doesn't matter how much you zoom in on it, it doesn't start looking like a straight line. So the idea of approximating what's going on with this graph with tangent line information doesn't even make any sense. What's the tangent line? Is it that one? Or that one? Or maybe I can make up some other straight lines that touch the graph at that point. There is no tangent line there in the usual sense of the word. The graph doesn't start looking like a particular straight line, no matter how much you zoom in. This time, the non-smoothness at t equals 0 is the fault of the graph. You can change parameters, you can do this, you can do that, but the graph is still going to be the same. It's still going to have that sharp corner on it. This is the other way that a graph can be non-smooth. We now know about graphs. in a way that corresponds to knowing about y equal f of x. If you look back at your calculus book, after you got done doing limits in Calc 1, what did you talk about? Derivatives, which were slopes of tangent lines. You also looked at concavity. So in the next discussion, we're going to talk about slopes of tangent lines for parametric equations. We'll at least look at second derivatives. We'll certainly look at arc length, and we may look at the area of surface of revolution, which is something that we haven't thought about since chapter 7. In the meantime, I hope everybody's doing well, and I'll talk to you in the next discussion.